Hi everyone, and welcome to the second of two videos going through the past exam questions on the topic of rate constants and temperature. Now, this question here is very similar to the questions in the first of these videos, but there is a little bit of extra stuff to it. Okay, if we have a look at this question, it's saying, again, a student has carried out an investigation to find the activation energy. Okay, we said that's usually the purpose of this type of question, is to work out what the activation energy is. But this question also introduces this idea of the pre-exponential factor, which we'll look at later on. So they've determined the rate constant at various different temperatures and plotted a graph of the natural log of K on the y-axis and 1 over the temperature on the x-axis. So this is very similar to the other question that we saw, and hopefully you'll get familiar with these types of questions. This is pretty much all they can ask you. Okay, so if you can make sure you can do this type of question, then you won't be surprised. You'll know what to expect in the exam. What do we need to do? We need to draw a line of best fit and calculate the activation energy. Okay. We mentioned that it is worth just taking a little bit of time to try to get your line of best fit as accurate as you possibly can. We talked about potentially putting the ruler up on its edge if that makes your life easier. Do that. So we're going to draw a line of best fit. And then what are we going to do with our line of best fit? Well, it goes back to the equation, doesn't it? Okay, remember they give you the equation, the Arrhenius equation, in both of its forms. This is the form that we're interested in because this equation is in the form of a straight line, y equals mx plus c. So I'm just going to write that out again so that we've got it here. And then if we rearrange it slightly, we're just going to split this term up. We can see much easier how it links to y equals mx plus c. And then hopefully we can see that the natural log of k is the y, clearly. The 1 over t is the x. So therefore this minus ea over r must be the m part, and then the plus natural log of a is the plus c part. Okay. M represents the gradient. Okay, so if we want to calculate the activation energy, the bit we're interested in is this minus ea over r part, and therefore the bit of the graph that we're interested in is the gradient. So we need to work out the gradient of this line that we've just drawn. We're going to calculate the gradient over the entire length of the graph as much as we can. We're not going to do a tiny little triangle here, because if we're slightly off with our reading, we're going to get it. It's going to make a big difference. So I'm going to use the whole graph. So I'm going to go and find where my y-intercept is up here. 31.1, 0.2, 0.3, 31.4. We've got there. And then if we go from the bottom of the graph here, where did we get to this point? Okay, and I'm just going to go across there. That comes out at 27.1, 27.2, 27.3. So our change in y is 31.4 minus 27.3, which is 4.1. And our change in x is all the way across, right? So from 0 to 5, but it's times 10 to the minus 3. Be really careful with this. This is very common, and it's very easily to miss that out. And then you're going to be a factor of 1,000 out. So be really careful with looking for that. So the change in x is 5 times 10 to the minus 3. Therefore, the gradient is going to be 4.1 divided by 5 times 10 to the minus 3. So if we calculate that, we end up with a gradient of 820. And we mentioned this in the first video, but look at the graph. The gradient is not 820, is it? It's minus 820. This is clearly a negative gradient. Okay, I feel like it's easier to do that than to try and carry a negative all the way through this calculation. Just calculate a number and then look at it and go, it's clearly supposed to be negative. Okay. So that is our gradient, which is the m. So therefore that is equal to minus ea over r. And therefore to calculate the activation energy, we need to multiply by r. Again, r is given to us on the data sheet. You'll hopefully get familiar with this. You've seen it before in the ideal gas equation. PV equals nRT, it's the same r. It's the gas constant, it's 8.314. So we just need to multiply this by 8.314. And so we end up with 6,817.48. And that is going to be equal to our activation energy. Okay, we've multiplied by R, and because there was a negative sign on both sides, we can just ignore the negative sign. Okay, and that's why it's important that you say that your gradient is minus 820. And then all we need to do is put it into 3 significant figures, and we need to think about the units. Okay, in the first video, it was asking us for the value of the activation energy in kilojoules per mole, which would mean that we would need to divide this value by 1,000. Okay, but in this question, it is asking for it in joules per mole. That is in joules per mole, so we don't need to do anything in terms of changing into the right units. We just need to put it to 3 significant figures. Okay, so we're going to call this 6,820. Okay. Right, this question then continues, and we're going to introduce this idea of the pre-exponential factor. Okay, so this is the other part that often crops up in these kind of questions. Okay, we've gone through 2 examples now of how to calculate the activation energy. How do we calculate this pre-exponential factor A? Okay, well, to be able to work out what we're supposed to do with that, again, we need to go back to our equation. Okay, so what does the equation say about A? Here we go. If this is our equation, we've linked it to y equals mx plus c. The A is linked to the c part of it. Okay, c, if you remember, represents the y-axis intercept. Okay, so therefore, the y-intercept of the graph is equal to the natural log of A. And we know what the y-intercept is. I actually measured that as part of working out the gradient. So we had 31.4 for our y-intercept. So therefore, the natural log of A is 31.4. But that's not what we want. We just want A. We don't want the natural log of it. And again, this might be a point that seems a bit intimidating to you if you're not comfortable with your maths. But again, in terms of how we actually do the question, yes, this might seem complicated, but in terms of what we actually need to do, it's really straightforward. You've got the natural log button on your calculator. We need to get rid of the natural log, so we need to do the inverse of that. Okay, the inverse of natural log is e to the power of. Okay, and it's the same button on your calculator, it's just the second function version. Okay, so all I'm going to do is shift, and we're going to do e to the power of 31.4. Okay, and so if we say that A is equal to e to the power of 31.4, which is 4.33 times 10 to the power of 13. And that's it. It's as simple as that. So even if you're not comfortable with what is all this business about e and logarithms and all this, what do you actually have to do? Press 2 buttons on your calculator, really. Okay, read off the y-axis intercept and do e to the power of that on your calculator. Okay. This question also comes up in the multiple choice section. If we have a look at this one, here we've got a graph again. Look, it's a graph of natural log of k against 1 over t. It's a straight line, so it's y equals mx plus c. It's a negative gradient. So you can see these questions are very, very similar every time. So hopefully you can get comfortable with them. And again, it's asking us what is the value of the pre-exponential factor. So we've got to do exactly the same as we just did on the previous question. Okay. What we're going to do, we're going to read off the y-axis intercept. Okay. So here this is 31.5. Do try and be accurate when you're reading this off. It is between 31 and 32. If you just go, oh, it's 31, you will end up with the wrong answer. So do try and be careful when you're reading off a scale. And you can see in the options that you've been given, they're going to try and catch you out. That is not the value of A, is it? Okay, 31.5 is the value of the natural logarithm of A. It's not A itself. Okay, so this is not correct, but a lot of people would fall for that one. And we need to do the same calculation that we did in the previous question. To get A, we need to do e to the power of 31.5. Okay, it's not just 31.5 itself. Okay. So again, we're just going to do the opposite of the natural logarithm button. And we end up with a number that's going to be similar to this. And if you think about what we did here, these 2 questions are off different papers. You wouldn't get them at the same time. But you can see that if that was the value for e to the power of 31.4, we're going to expect something similar to that, aren't we? Okay, it is always useful to try and think about what kind of number you're expecting. So here we're going to say this is 4.79 times 10 to the power of 13. And so therefore the answer is D.